Okay, so welcome to lecture 27. We've been deriving the equations for the chaotic water wheel that's ultimately going to lead to the Lorentz equations. And so in the previous lecture, we looked at the conservation of mass around this water wheel, and we basically showed that for the water wheel, instantaneously the change in mass of a sector of the water wheel is the amount of stuff you're pumping in minus the amount of stuff that's leaking out, minus the amount of stuff that's rotating in from the one side, plus the amount of stuff that's rotating in, minus the amount of stuff that's rotating out, because we viewed the function in the fixed frame, in other words, in the lab frame. And ultimately, we came up with this conservation of mass, or sometimes I call it also the continuity equation. Okay, and so the ones that we're going to derive today is an equation that comes from the equivalent of Newton's laws. Okay, so the one basically ensures that mass isn't created or destroyed. The second one is going to describe the dynamics for the water wheel. And if you remember correctly, I said there were two things, two unknowns. The one was the mass distribution, in other words, how the water was distributed around the water wheel. And the second one was basically how rapidly the water wheel was rotating, right? So if you pump a whole bunch of water in at the top, then it's going to want to swing round, and the mass distribution is not going to be even. And the frequency with which it swings round is that the omega t. So what I'm going to do today is actually have a look at the equivalent of Newton's laws for the water wheel. And what that is, it's basically what we call the torque balance equation. So if you think of Newton's laws, I don't know how carefully you've looked at them, but usually it's this F equals to ma. And then people studied this and they said, generally an object has two types of motion. The one is the linear motion where you go straight or turn around, and the other one is rotational motion. And the fundamental law of mechanics is actually to split Newton's law up into two things. So in physics, you actually learn them as two separate things, but they actually all follow from the three-dimensional version of F equals to ma. Okay? So the normal projectile motion you do in physics is the momentum of the center of mass. The things that you do with torque, where you have the wheels turning and stuff, is also Newton's law, but it is simply the component that's rotating. Okay, and the fundamental law of mechanics basically says that these two things decouple in Newtonian physics, not in other fields. Okay, so what we're going to look at today is Newton's law, and because we have this water wheel that's around, basically rotating around an axis, we only have to worry about the torque balance part, right? On average, the center of mass of the water wheel is going nowhere. Well, it's staying exactly where it's centered, but the torque is changing, okay? And the torque is being changed by this water that's pumped in at the top and then moves around, and we want to write down the equations for that. Okay, so let I be the moment of inertia for the water wheel, okay? And then you can express, we know that it depends on t, okay? Because remember, the moment of inertia is dependent on the mass as well as the mass distribution from a particular axis. And because the amount of water in each of these little things is changing, our moment of inertia is dependent on time, okay, because the water distribution does, okay. And then the torque balance equation is basically the rate of change of the moment of inertia times omega, or times the frequency with which it's rotating. And that is just Newton's law, and we can therefore write it down as a component that's the damping, okay, which I'm going to discuss now, and a component which is the gravitational torque, right? So gravity is making the wheel spin every time the heavy water falls from the top where it's pumped in down, and so that's the one component. The second component is the damping component, and for the damping component, we can always write it as some constant nu times omega, right? So like any type of damping we've looked at, or linear damping we've looked up until this point, it's simply always something times w or y dot. The same thing is here. It's something times some constant times the velocity. And where the damping comes from is actually two places. Hidden in that equation, there are actually two contributions. Unfortunately, they have the same form, so we can only write one term down. So the contributions is, one, we have this wheel rotating around an axis, and we've got a brake on here, right, that we can set. So we can actually add friction. So that's the one thing that slows the wheel down. But there's another thing that's more subtle, and it has exactly the same contribution, but it's worthwhile mentioning. The second thing is what they call inertial damping. It's something, have you ever jumped onto a merry-go-round? You know, these things that spin in the kids' thing? Okay, you jump on, and then you get on, and when you're jumping on, you're actually slowing down the merry-go-round because it's got angular momentum, and you jump on, you've got none. So you actually take some of it because you know the whole thing is heavier, and it slows it down. Similarly, if you're sitting on it, right, have you ever stood on it and your big brother or somebody has like spun it really, really fast, and you then jump off? Then when you hit the ground, if you're not running, you're actually going to fall because you jump off with a speed. Okay, so what happens with the inertial damping is the water actually, when it is pumped in, it falls straight down, and it has no angular momentum. Okay, so when it comes on, it has no angular momentum, and when it leaks out, the velocity is the velocity of the component in the rotational direction is the same as that water wheel, so it actually has angular momentum when it leaks out. And so what happens is this jumping on with no angular momentum and then leaking out with some angular momentum results in the actual thing rotating slower. And so even if the pivot was frictionless, the thing would still slow down simply because the water is leaking out. Okay, so the only reason we don't say it explicitly is because it has exactly the same form as the brake. Okay, but it's important to note, even if the brake is off, you're still going to have damping, and that damping is going to come from the fact that your water has lost angular momentum. Okay, so the minimum amount of damping you're going to get into the system is basically this loss of angular momentum due to the water coming in with no angular momentum and then leaking out at the end. Okay, so that's a form of friction. So that's our damping term. Okay, that's basically what slows this thing down. The term that actually drives the change in torque is our gravitational torque. Okay, and that one I'm going to derive for you now. A way of thinking about it, remember I said we have this wheel that's rotating and we can set the tilt angle, okay? And so let's just, to begin the discussion, move the wheel that is like standing vertically. So you have this wheel and somehow the water's getting in, and then when the water gets in, it like spins around, but it's almost vertical. And if you do that, remember I said our angle theta goes from the highest point down to wherever else. So theta equals to 0 is the highest point of the tilt. That's our definition that we gave in the last time. So let's do that and think about it as a steering wheel. So when theta is equals to 0, okay, suppose you're at this angle and there's a thing of water here. It's like a pendulum standing on the pendulum standing up there. It actually does exert no force on your steering wheel. Like if you have a steering wheel and you just hold it at the top and pull it down, you're not going to steer anywhere. Okay, so a container of water, a little bit of water over there, is not going to cause the wheel to rotate. But what happens if you move the water out at an angle that's no longer vertical over there, and you put a packet of water over there? What's going to happen is the gravity is going to pull it down, and it's going to cause the wheel to rotate in the counterclockwise direction. Okay, so there's a force the moment the water goes off the vertical. And if you go even further, so suppose we're now at the theta angle for which I'm going to derive it, you have a packet of water there, let's say d theta, the contribution of this bit of water is going to be to pull the wheel down quite fast. So the maximum amount of added torque you can have is if you're 90 degrees over there. So let's just write that down mathematically. Okay, so for our little sector there, the mass in that sector, the mass is simply the mass there times d theta because it's infinitesimal angle, and this is your mass distribution. Remember how the mass is distributed over theta. So the total amount of mass that I've depicted there is simply m times d theta. The torque that's exerted is basically the acceleration or the effective acceleration due to gravity times dm, the mass that it's pulling on, times r sine theta. Okay, and if you did physics, you can see all this r sine theta does was simply capture this fact that the angle is important. It comes from the torque that has the curl of the radius times the force. Okay, so that's effectively where the sine theta comes from. I just tried to give you an intuitive picture over here of what it is. So the infinitesimal torque exerted by this little dark blue packet of water is just g dm r sine theta. Okay, and you need to be careful with this g. It's the effective gravitational acceleration. Okay, so it's the part of the acceleration that pulls at 90 degrees with the axis. So for example, suppose we had the side view and this wheel is no longer 100% vertical but at an angle, right? So suppose we've taken that wheel thing that's rotating and we've put it at a specific angle, then, and we're going to call that angle the tilt angle alpha, then there's a component of gravity, right, g0, that always pulls straight down, which is the normal gravitational acceleration. But the only part that's important for us is actually the force that's being exerted at 90 degrees to the axis. So that's this g effective, which is basically g0 times sine alpha. In other words, the component of g0 that lies within the plane that the thing is rotating. Okay, so you can see by effectively changing alpha over here, you're going to change the strength of the impact of the gravitational force on the actual dynamics of your wheel. Okay, and so if alpha is vertical, like I said to you to imagine it to start with, then alpha is just 2 pi over 2, and it's just g0. But as I move the thing flatter and flatter, in other words, I change the tilt angle to 0, the impact of gravity becomes less and less important. And in fact, when the tilt angle is 0, there is nothing that's causing the wheel to rotate because the water just sits there and leaks out. Okay, so it's just to give you an intuitive feeling of where that comes from. So our torque now we can get by integrating this equation, and it's important to note that the rotation, the torque increases the rotation, and theta therefore, provided sine theta is positive. Okay, so it's just saying that this thing tends to pull it down, so it increases the rotation that way around. If you were to have a mass over here, it would actually try and decrease omega. Okay, so it's just to give you an idea of how the sines works. So what we do now to write down the total amount of torque, because the wheel rotates, you have to work out the torque on the whole wheel because the wheel is rigid and it rotates, and that's the only thing you're measuring is what this rotation is like, is you simply have to integrate over the contribution of all the individual parts of the torque. Okay, and so you have that you take out your constant g, which is just g0 sine alpha, times r, which is the average radius of the circle, and then the integral over 2 pi of the mass distribution times sine theta d theta. Okay, so that's the torque expression. And so what the final torque balance equation is, which is basically Newton's law for this wheel, is just ddt of the moment of inertia times omega, which is equals to a constant times minus a constant times omega plus this effective force or the torque that gravity is pulling on the wheel with. Okay, right. So that's our second equation. So let's go ahead and see how we go and solve both these two equations together. In other words, the mass conservation and this torque equation, and how we eventually end up at having our set of equations that looks like the Lorentz equations. Okay. So let me just summarize them over here. So our set of equations governing the water wheel are one, conservation of mass, which I derived in the previous lecture. So there we go. And you can see the things that enter it is basically the mass distribution over there and omega t, and all the other things are constants, and it's dependent both on theta and on time. Okay, the second equation we have to solve is the torque balance equation. Okay, and what that is basically the damping plus this thing that we've just derived over there that's due to gravity. And so the first step in solving this is to note that the moment of inertia approaches a constant as t approaches to infinity. I can prove it. I'm not going to prove it initially. I'm just going to use it as a simplifying thing. So the moment of inertia is basically the distribution of mass around the center, around the axes. And that thing goes to a constant even if omega t, in other words, the rotation is chaotic. Okay, so this might be difficult. It is conceptually difficult, but it is an assumption we're going to make the equations easier, and I'm going to prove it to you at a later point. Okay, but it's just something to remember. So we can basically treat I of t, if it returns to me, as a constant. Okay, and if you do that, you can get your first simplification, because you can take the I of t, the moment of inertia, which is not obvious that it's a constant, you can take it out of this equation, and instead of solving this thing, which is slightly more nonlinear, you can basically solve this equation over here. Okay? And you can know that the answer you get is valid only as t approaches to infinity. So initially, if you remember the video that I showed the last time of Strogatz starting the thing up, where he pumped the water in, the air, initially it wasn't constant, but after like a couple of minutes, the moment of inertia actually does approach a constant. Okay? This thing, they call an Intergrade differential equation. In other words, there's an integral in the derivative within the equation as well. I don't know if you've seen this before. Have you seen something like that before? Maybe in the second year. I know it was briefly mentioned when I was a student, but nobody ever told me how to solve it. But anyway, that's what its name is if you want to look at it at other times, sort of look it up. So now what we want to do is actually we want to go ahead and we want to solve both these two at the same time. And I don't expect you to solve this from scratch, but I do think it's very interesting to actually see the method that was used, because it's been used in a number of other places as well, especially if you're going to start doing more complicated modeling. Okay, so the first thing we note is the symmetry of the problem. M of theta t, okay, is 2 pi periodic in theta, right? Because the mass distribution, once you've gone round, you get the same one repeated. And so the moment you have something that's 2 pi periodic, you can actually express it as a Fourier series, okay? So we can, the moment it's 2 pi periodic, we're going to assume that m of theta of t we can express in the following way. We can say it's some coefficient that's dependent on time, which basically tells me the amplitude of that thing, multiplied by sine n theta plus a different coefficient, bnt, multiplying cos n theta, and I'm going to look over all possible harmonics of theta. So I've basically made a decomposition of this m in terms of its sine and its cosine components. Okay? And then, so I'm going to make this ansatz, which I can always do, and there are theorems that show it's convergent and all those nice things. I'm going to make this assumption for m of theta and t, and then I'm going to go about and derive equations for the amplitudes a n of t and b n of t. So for these two things. Just one more step that we need is we need to be able to solve this equation, we need to know what Q is. And the only thing I'm going to assume is that water is added symmetrically above theta. And therefore, there's no sine component. Okay, so I'm going to be able to write Q as a composition of symmetric functions that are also periodic in 2 pi. Okay, so there's going to be an expansion over there for Q of theta. And this is very frustrating that it does this. Okay, and where Qn are also constants that I know. So I basically can take a Fourier series transform of the way in which Q is appearing, and I can always write it as a series. And what I do now is I take both these two guys, these two expressions or series expansions for my functions, and I put it back into this equation for the conservation of mass. And then the thing explodes, basically. But it's important to do it systematically, and even though it looks very complicated, it's going to yield a very, very simple answer. So what I have now is that the time derivative of your mass of t, this is the first term, and I've just substituted the whole series in here, is equals to, sorry, just hold on, this is going to drive me nuts. Let's see if I can get rid of the noise. Okay, so he said it will only be 2 more minutes of torture. So I've substituted our ansatz for m in over there. I'm going to substitute, just because my space doesn't work out otherwise, I'm going to substitute it in there. So I have minus k times this whole big series. And this q, this driving term, I've put in there, so there's my infinite series for Q. And then finally, I have this omega times dd theta, so the dd theta is still out front there, of this thing. Okay? So how does this make things simpler? Well, the one thing is, if you take this expression and you take the integral of sine m of theta with it, you can see you're going to kill everything except sine m of theta terms. Okay. So because you have, if you take the integral of cos m of theta between 0 and 2 pi with this expression, you're going to kill everything except that particular cos term, or the coefficients of that cos term. So you have this orthogonality property where you basically can extract the coefficients of sine n of theta and cos n of theta and solve those independently. So you've replaced this big differential equation simply with the coefficients of sine n of theta and cos n of theta. It was very, very similar to the technique that we were using when we were actually doing the perturbation theory. Okay, so you basically just take the inner product of this whole expression with sine of theta or with cos of theta, and you look at what's left, and those then become the equations. So let's look at what we get. So suppose we want to look at the coefficients of sine n of theta, right? So what we do is we go in here, we simply have on the right-hand side, we have a n of t times d dt of that thing. So we have a n dot, okay? And this is cos, so it disappears. And then we have the sine n term, it's minus k times a n of t. That comes from there. From over here, there's no sine term, so that falls away. Over here, we have to be careful because we first have to take the derivative. So my sine term comes from over here because basically d d theta of cos n pi theta is minus n times sine n theta. So what we have is our bn times omega times minus n. So we have this plus bn term. Okay, so, and that's it. So we now have an ordinary differential equation for a of n. We can do the same thing when we look at the cos n theta term, right? So here we have basically d dt of bn of t. And we have that is equals to the bn term, so it's minus k bn coming out there. And now this thing becomes important, the place where we're pouring in the water. So how we're pouring in the water becomes important. So we have the qn term coming in here. And then finally, we have the derivative of sine is just sine n pi is just in cos n pi. So we have minus omega a n times n. Okay, so what this thing basically permits us, and we must note that we have n going from 0 to infinity. And so what we've done is we've basically, because we made this assumption, we've basically solved a whole bunch, got an infinite system of coupled ordinary differential equations that we want to solve. And the moment we get an, and these things define what an and bn are, the moment we know what an is a function of t and bn as a function of t is, we put it back in here, and then we have the answer for m. And you can say, okay, you must be kidding me. You promised me to do Lorenz's equation in 3 dimensions, and we've now ended up with an infinite set, and you've just made my life more miserable than you could possibly imagine. And the answer is no. We need a miracle, but we do get a miracle. Okay. So do you have questions about it at this point? I don't expect you to do it. I expect you to know that something like this exists. Okay. And that if ever you get a problem like this, you know what things to start trying. Those convection rolls I showed you in the previous lecture, when they analyze it, they do something very similar. This type of analysis is also what Lorentz did originally for his convection rolls, just a little bit more complicated. And they call it a normal mode analysis, where you basically guess, or not guess, make a motivated guess. There are ways of guessing it. Basically, for this one function, you expand it in a whole bunch of functions that are orthogonal, and then you solve for how the coefficients evolve in time. Okay, so I'm going to stop the basically the recording part, because that's where my